Welcome to EconTalk, part of the Library of Economics and Liberty. I'm your host, Russ Roberts of George Mason University and Stanford University's Hoover Institution. Our website is econtalk.org, where you can subscribe, find other episodes, comment on this podcast, and find links and other information related to today's conversation. Our email address is mail@econtalk.org. We'd love to hear from you. Today is May 2nd, 2011, and my guest is William Byers of Concordia University. His latest book is The Blind Spot, Science and the Crisis of Uncertainty. William, welcome to EconTalk.
Thanks, Russ. Thanks for inviting me.
So, what is the blind spot? What is the blind spot of science? And what do you mean by it?
Well, I guess it is the notion that models or mathematics or theories captures reality completely, and that it's sort of an absolute accurate picture of what's going on, and that in its most general. And I go on to talk about the nature of our rational consciousness, if you will. This idea that it can, in fact, provide us with information, which is I'm not saying the information is not useful, but the idea that it provides information which is absolute, objective, and will never be changed, that is a blind spot for me.
And, of course, that is the way I think a lot of lay people and some scientists and social scientists think about their disciplines, right? It just we just push forward and we eliminate ignorance and light up the darkness as we move along, and it's just a matter of time before we figure everything out. And you're pursuing you're suggesting that's a little bit incorrect.
Well, I myself think it's simplistic. You know, even in the book, I draw this analogy of the one that you mentioned, that we think that science proceeds as though you're exploring some new territory and you just sort of conquer one bit of territory and you move on to the next. I claim that actually you never totally conquer any territory. You can always come back to questions which were raised in science in the past and understand them from a different direction, understand them deeper. This happens all the time when, often we understand something within from a certain perspective, with a certain paradigm in mind. And when the paradigm changes, we go back to the old things that we were talking about and find that, wow, they look different.
Yeah, I was struck by that. In fact, early on in the book, you talk about the elusiveness, is the way I think of it, the elusiveness of deep concepts. And one example you give is randomness. And you say you can look up a definition of randomness in the dictionary, but you never really understand it. You can always go deeper. Talk about that idea.
Well, randomness is a wonderful idea. I love it myself, and I did when I started to think about it. I've now written about it in various ways in two books, and I did originally consult many of my mathematical colleagues, especially statisticians and probabilists, who use it as a kind of foundation concept in their subjects, And I asked them, what is randomness? And it was interesting. It's almost an embarrassing question, because people have a lot of trouble making that concept concrete. Okay, so everyone, on some informal level, everyone knows what it means, but on a very concrete mathematical level, there are actually multiple definitions of randomness, and I want to say not only do people not agree on what randomness is, I want to say that it means something slightly different as you move from discipline to discipline, from the theory of evolution, for example, to a kind of a analysis of the validity of an experiment, to what the IBM researcher Gregory Chaitin calls algorithmic randomness. Everyone's using the same word, but everyone's using it in a slightly different way. And the thing about randomness, which is so really interesting, at least my point is, it's kind of like an endless, an infinite progression. You can always understand randomness better because it seems to me that there is a sort of primal randomness which in a certain sense is inarticulate. And once you articulate it, well, then you're talking about articulated randomness. And that has a definition, and you can work with that definition, and you can do wonderful things sometimes with it. But it's always possible, because randomness is that kind of open-ended concept, you can always go back to it and look at it from another direction, theory. And, you know, a lot depends on what you're interested in and what use you're making of that concept. So this notion that even mathematical concepts are, in some sense, open-ended in that way, I don't think that is the normal way that people think about mathematics.
Here's what you wrote in the book. I'm going to read a somewhat lengthy quote, and I'm going to skip a sentence or two in the middle, but forgive me, but I think it'll flow easily. Quote, "You cannot understand a definition by parsing it. You acquire an understanding by working with the definition in many different circumstances, by thinking about it, by solving problems involving the concept, and by making mistakes and learning from those mistakes. Understanding is a process without end. At a certain stage in the process, one can say, I understand randomness. But in reality, you can always understand it better, understand it differently. The better you understand it, the more grounded you are in the primal notion. Randomness is not a thing. In a way, it does not exist. It is open and inevitably complete." And then you go, there's a couple sentences and you continue. "An explicit formulation is not the definition, but should be thought of as an entry point, the beginning of an exploration. We then work with this tentative definition, trying to expand our understanding. We do this by exploring in two directions simultaneously: backward, by evoking the informal situation out of which it arose; forward, by exploring examples and consequences. In the process of this exploration, our understanding will be expanded and made subtler. This process may then be iterated a number of times." And of course, you're referring to mathematics, you're referring to probability theory, you're referring to statistics and science. But in economics, I've been struck, and the reason I underlined that passage in the book, and it really rang true to me and very deeply, is that for me there are a handful of concepts in economics that are primal that I feel the same way about. They are deep, they can be explored over and over again, and I find that my own understanding expands. Even when I think I understand it fairly well, I always find there's more to learn. I just want to give a couple examples of that, which listeners will be familiar with perhaps from previous programs. But in the Wealth of Nations, Adam Smith, it's a book written 1776. You'd think we'd kind of mastered it by now and those ideas, but he writes in there about the division of labor and exchange and trade. And I find that concept, you can squeeze it into a 2x2 table, and you can talk about gains from trade. You can draw a little diagram about it. But for me, it is a rich concept that I'm always finding I can go a little bit deeper. Another example, which we'll come back to, I hope, is emergent order, the idea of complexity, which you write about later in the book and in science. But, of course, it's a very important concept in economics. And it's implicit in Adam Smith. It's the idea of the invisible hand. But the way it's been used in economics in the modern era by Hayek and others is such a deep concept for me that I learn something new about it. I feel like every week or month I see it in different guises. I see it from different perspectives. It's richer to me than it was when I first thought about it 5, 10, 15 years ago. And I just think that way of thinking about science and understanding and depth is just so valuable.
It's interesting, and I think you put your finger on a key point. In this entire book, I basically sort of, in part rhetorically, compare different attitudes that one can have towards science. And this latter attitude, the exploration attitude, is an attitude which regards science as a continual work in progress. And often one thinks of that in terms of the extent of science, that there's more stuff to learn, but that what we know, we know. But I guess what I'm saying is what you repeated, that in science we actually work, as we do in mathematics, with terms which are undefined, but that doesn't mean that we're totally ignorant of them. Terms like, I don't know, time and space and number, and these things do not have precise definitions. We have some sort of response to these things, and we have a great deal of experience with them. But the idea that they're closed, that science is closed, even that an area of science is closed, I think actually is a dangerous idea. And I recommend this kind of open-ended idea that one explores a discipline, and then one can always explore further. That gives us a totally different attitude towards the results that we get and the systems that we create.
Yeah, talk about another way you frame this in the book is you contrast a science of wonder with a science of certainty. Talk about that distinction.
Well, in fact, we've just been talking to it, and you cleverly led me up to this. In fact, the science of certainty is the idea that the theory is identical to what it's a theory of, and that the two fit so that, if you have a theory, a Newtonian theory of mechanics, that actually is the world in a certain sense, that the theory is interchangeable with the world, and it's over. A theory of wonder, of course, is a theory that one is an explorer, one loves the terrain, one loves what one does, and one's trying to get deep insights into the nature of whatever reality it is that your particular discipline is involved with. And that one emphasizes, I think these attitudes are considerably different. The science of wonder emphasizes that science is unending creativity. The science of certainty emphasizes that one day we'll all be replaced with machines or supercomputers that will, in fact, be programmed with the latest theory, and we can stand back, and human beings will not be needed anymore because the theory is just so absolutely perfect and complete.
Yes,
I think that's an illusion. I think it's an illusion and a mythology that has existed since the time of the ancient Greeks, that people had this dream. I call it the dream of reason, that we can totally capture reality, pin it down.
My colleague here, George Mason, Robin Hansen, was on this program a few months back, and he said, the brain is just chemistry. So it's simply a matter of time before we figure it all out, and then we'll be able to exploit machinery and technology to create better and bigger brains. It's the idea behind the singularity concept, the technological singularity, this idea that there's going to be this enormous explosion in technological ability once we can mimic a brain with a computer. I take it you're a skeptic about that.
Totally. I'm totally skeptical. And what I do is I trace that dream back. And I think it first emerged in ancient Greece, in mathematics and in Euclidean geometry. The idea that we could, in fact, capture things like this. I just actually think, people think this is remarkably new, but actually it's an old mythology, but it's got a new technological manifestation, namely the computer. And now we're in love with computers and we think that their potentials are limitless. I always think that all the technology that we create basically is not really new. What it does, it takes a certain human ability and it accelerates it or amplifies it. So a telescope amplifies, the sense of sight. And a computer amplifies our rational faculties. My claim is that human intelligence is more than reason. Reason is, of course, important, but human beings are larger than reason. I remember recently in the Times, David Brooks had a column where I think it was called The New Humanism, where he claimed that one of the problems with our culture was this over-reliance on rationality. In his words, it was to the detriment of things like emotion. But I would say in general, because we believe so strongly in this kind of what I call a mythology, this mythology that the machines are coming down the line that will totally replace human beings and all, we tend to downgrade human capacities. We don't realize that when we have a model, we feel in some sense that it will replace human qualities like judgment. In my mind, you can never replace human judgment. And so I guess I'm operating from what you might call a humanistic perspective, which says that computers are wonderful. I love mine, but they're intrinsically limited in what they can do. I think it's just I would think your colleague. What could I say to him? In my mind, it's purely a projection of a certain kind of human inability to deal with uncertainty.
Well, let me play Robin for a minute, which is
sure.
I'm a little uneasy about for all kinds of reasons. But let me play Robin for a minute. One of the things I asked him was, is a computer going to create Beethoven's 10th Symphony? What is the role for artistic and other types of creativity? And I think people like Robin and others would say, well, we romanticize that. It's still just neurons firing. It's still, a great chess player we think of as an artistic genius, but a great computer is now pretty much surpassed almost all of the great chess players. And it's just, again, a matter of romance about and time before we eliminate this idea that there's something more than the brain.
Well, I have a number of comments, but one is that when we say, to take the particular example that people always use, that computers play great chess, first of all, I would claim that there are actually two games there. There's computer chess and human chess, and it isn't exactly the same game. Okay, humans play chess very differently than computers play chess. Okay, so in a certain sense, you're comparing apples with oranges when you claim that. And the second point is
you want to stop and explain that, because I think I know what you mean.
Well, you see, what happens is computers, because they have such a large memory capacity and they do very simple operations so quickly, they can go through literally billions of possibilities in a very, very short amount of time. Human beings cannot do that. So they have to rely on other capacities that they have that the computer doesn't have. Things like intuition and judgment and feel. Things which are difficult to quantify. In fact, human beings have all these capacities which are essentially non-quantifiable. That is to say, we have parts of our brains that operate, non-digitally.
So I'm going to derail you for a minute here because I think it's such an important point. You give an example in the book of idiot savants, people who can multiply large numbers instantly, can see patterns in numbers very instantaneously. And I think the assumption of many is that, well, they just have a really good hard drive. They're just doing the calculations really fast. But your point is that, no, they're not. They're doing a different thing. They're not going digit by digit and doing multiplication or going and looking for prime numbers or other factors or things like that.
It seems to be true from the reading that I've done that and the testimony, some of which is in the book, of people who are savants but not idiots. That is to say, who have high intelligence but also have savant abilities, and there have been a lot of scientists like this. And these people testify actually that they think differently about numbers than probably you and I think about numbers. And I raise this question.
Certainly than I do. You can be in that group if you want.
I give that as an example of this wonderful Indian mathematician Ramanujan, who had this, what could you say? He seemed to have this feel for numbers, like very large numbers were like people to him. They had individual personalities, And
you want to tell that story about, do you have that story when he was visited in the hospital by Hardy?
That's the story, but when he was visited in the hospital by Hardy and he asks him about the number on his taxi, and Hardy says, I think he says it's 1729, not a particularly interesting number, and Ramanujan says, immediately, on the contrary, it's the smallest number that can be written as the sum of two cubes in two different ways.
Which is unbelievable, right? Literally,
well, think
unbelievable.
About what an intimacy that man had with the natural numbers.
So the question about that example is, when he heard the number 1729, was that a number that he had looked at before? I mean, if you ask me, is 13 a prime number? I say, sure it is, because I know that. I don't have to think, let's see, what goes into 13? Is it 6 and 11? No. Okay, it's prime.
Right.
But 1729, had he thought about that before, or did he see it in a flash? It seems like a cheap parlor trick, right? It seems like Hardy, texted him before he got there and said, I'm in cab 1729. Make sure you can think of something cute for me when I get there. And that's not what he did, but was it just something that he saw instantly? Or
of course, this is pure speculation on my part. But let me give you another example, which is in one of Oliver Sacks's books, I think, about idiot savants who were really idiots. That is to say, they had low IQs of approximately 60 or less. And these people could tell you whether a 6-digit number was prime or not. So, in fact, the way Sacks describes these two twins, elderly twins who were his patients, they didn't really even have a concept of what multiplication or division was. And yet, they could say, and not instantaneously, actually, somehow, there was some process that went on, but there was clearly not dividing by every lower prime number. Something was happening which allowed them to draw the correct inferences. But, so I just think myself that number is one of those really primal concepts. I think it's primal not only in mathematics, but in every area that when mathematics is used. It's sort of what I say, it's something very basic. It's connected to our ability to make order out of the world, which is what an intelligence does. And mathematics is connected to that ability to order our experience. And clearly, it's built into us genetically in some very basic way. And when you study these idiot savants, you realize that perhaps there is another form of intelligence that they have access to, since the normal intelligence, let's say, that's measured by an IQ, is clearly deficient in these people. Now, it's interesting to speculate, and I think what happens in some very great mathematicians, people with these, that they have. If there is more than one form of intelligence, they have both forms of intelligence that have evolved to a very great degree. But, everyone has, when you do research, you have a mental map of what's going on, and not everyone has the same mental map. Not everyone has the same picture of a very complex situation. There are people who, I know when you do research, that there are people who have much more subtle, much richer interior mental intuitions of a situation than others.
Yeah, of course, this kind of talk creeps some people out. Not me, but it does make some people very uneasy because it sounds mystical, a little bit like religion. You're suggesting there's something supra-rational about supernatural about our abilities.
Oh no, I'm not saying that at all. I'm just saying that we have different mental abilities, and I'm advocating that we tap all of our mental abilities, not just one. As a matter of fact, if you want to have a very simple way of talking about it, which I mentioned in the book, which is also you can think about as left versus right-brained abilities. That in fact, when we talk about intelligence, we usually talk about the left brain.
Yep.
But that the right brain is also kind of functional, but produces, some people think that it's one side is more like digital and the other side is more like analog.
But that's just a vague way to try to grab, those are just words, as we've been saying, that don't really have clear meanings.
It is, in fact, but deep intuition is a fact. And, I think you said that some things just sound mystical. I think sometimes mystical is a word that's used in situations where there is a limitation on the rational intelligence. That's to say, if things can't be reduced to a kind of rational system, then that by definition is mystical, I don't think necessarily it's mystical at all in the sense of being otherworldly. It just means that the brain is more complicated than we think it is.
Or that certain aspects, as you talk about many times in the book, certain aspects of reality are not amenable to what we think of as the standard techniques of logic or certainty.
Well, we started to talk about this when we said that things like randomness or continuity don't have definitive definitions. Right? So we're talking about that even randomness is open-ended in this way. Right? That doesn't mean that you don't try to define randomness. Of course you try to define randomness. And every time you get it, if you get a really good definition, you get a really good theory as a consequence. And that helps you do what you want to do. And I have no objection, certainly. But you know that you could come back one day because you're interested in something else and get another definition of randomness. A lot of the definitions of randomness are connected to games of chance, were originally.
Yeah.
But with the advent of the computer, these other ideas like algorithmic randomness were invented. It's in response to a new problem. You revisited this idea of what does it mean? What does chance really mean? And when you think about it,
it's such a subtle idea.
It's such a subtle idea, exactly.
And I think that, again, I want to just come back to that because I think it's so powerful. The idea that by defining it, you then say, well, I understand it now, suggests a recipe-like cookbook nature to reality, which is certainly not true. I remember giving a talk on emergent order and economics to a group of economists, and it fell incredibly flat. They were totally unimpressed. And they said, well, we know all that. We know that, there's complexity in the world. But I wanted to say, but you don't. It's so rich. You don't see it the way I do. And it raises a question. I want to shift gears for a minute and talk about teaching, which is not something you talk about in the book particularly. But as a teacher in economics, I'm often torn between the science of wonder and the science of certainty. It's very tempting to teach equations and graphs with neat, clean answers that make for good exam questions. But as I get older, I find myself increasingly interested in conveying a sense of wonder. So when I talk about the price system, which Hayek, by the way, called a marvel, really capturing your concept of the science of wonder, it's much, I think, deeper and more important for my students to be amazed by the price system than to be able to answer an exam question about it. But then again, I have to give exams. And so pedagogically, I'd love to give a set of wonderful lectures rather than analytical lectures. So I do a mix of both. But I'm curious if that tension arises in your teaching in mathematics, because my wife's a math teacher and she and I talk about these issues all the time. I'd like to get your thoughts.
Absolutely. Absolutely. In fact, mathematics is, in a way, a very difficult field because for many, many years, the ongoing general philosophy of mathematics was something that was called formalism, which said essentially that mathematics is nothing but its formal content. It's theorems and definitions and proofs.
Yeah.
And when you proceed in that kind of very formal way, of course it's easy from the point of view of setting examinations. But you find after a while, 2 weeks after the final exam, when you bump into your students and realize that they don't recall a thing of what's happened all semester, that you failed to give them a grounding in the fundamental concepts, which will allow them to develop a kind of intuitive feel for the formalism they're dealing with. So my answer is, if you don't develop the other, and I grant that this makes teaching into an art and not a science. It's just easy to convey the facts, but it's hard to convey the wonder of the situation, how remarkable it is, and even in mathematics, that these are problems that actually intelligent human beings found intellectually exciting and stimulating, and not just a set of techniques that you have to memorize.
Or a set of blocks you have to arrange in a certain order to create, like it's like building a Lego house. You just kind of, you just, like a proof is just, you just do the different steps, one follows from another, and when you're done, you have a house. And I think you lose the poetry of the discipline for sure.
Well, that's precisely my point. In my first book, which was about mathematics, I made this point about that notion that even every proof is based on an idea. Often we think there's a certain finite. You mentioned this wonderful analogy of a Lego system. We think of it as kind of a Lego system, but actually, if you look carefully at any argument in any subject, you see that in fact it's built around an idea. If you've got the idea, in my opinion, you can forget about the details and reconstruct the argument. But when you study a subject from a formal point of view, no one tells you what the ideas are.
Yeah, funny how that works. Yeah, right. Well, that's something you talk about and evoke very nicely, which is the sense of exploration, the sense of discovery. Obviously, if someone tells you how to get from A to B, it looks rather mundane. You just go here, take a left here, take a right there. But for the actual journey, the person who first mapped it out, it's really something that it's almost an unparalleled human experience. Let me try to give I'll give a math example of it. One of the most beautiful things that I've ever seen is the documentary on Andrew Wiles' proof of Fermat's last theorem.
Right.
And it tries to capture, and it does it imperfectly, because the irony of all this, of course, is that it can't be captured perfectly. That's almost what we're saying. But it captures almost perfectly, or tries to give you the flavor of that creative endeavor. And it can't. But it gives you the flavor of it. It gives you a sense of it. And I find it so moving. I mean, it's a beautiful story. There's a lot of poetry to the story. But it moves me close to tears when I watch it, because there is something extraordinarily human and unique about that form of creativity. And it's true in every field. It's true. It's not as dramatic in economics, but it's in economics. It's in science, obviously. It's in art. It's in music. When you see something you haven't seen before, when you solve a puzzle that you thought you might not solve, there is something, that emotion and the power of that is something intrinsic in our humanity that not everybody has the gift of being able to do it, obviously. But those who do, it's just an extraordinary thing.
Of course, I couldn't agree more. And I think it's interesting that you were talking about teaching, and we've moved into talking about creativity. But for me, learning, when a student learns, they kind of recapitulate. They go through the same stages. They're as the people who created the subject. It's not. I don't like the idea that it's just a whole bunch of geniuses who can be creative, and that the average person has no access to that. Because it seems to me that when you're describing your emotional response to a situation of major creativity, in fact, in some sense, that is a resonance
that what? I'm sorry,
with the original creativity.
I lost you there for a sec. You say that does what?
It resonates. Your experience resonates with the creativity of the situation.
Yeah.
It is not different. It is, of course, not of the same depth.
Right.
But the idea that you can appreciate means that something in you goes off, and you say, aha, I know what that is on some level. And that reaction, of course, is not an intellectual reaction. It's some very, very deep reaction. One is moved by these stories of extraordinary creativity, even if one understands them imperfectly, as everyone does with Wiles' proof. But I think myself that there is something about creativity which is self-validating. You don't have to ask why. You just have to observe your own reaction to that situation. And I think that if learning is then everyone is creative.
If learning is what?
If learning is at basis a form of creativity and not just a form of amassing facts.
Yeah.
You know, if it's not a Lego, but it's actually a creative experience, and that's my feeling, that if there is no creative insight, when a student is learning something, if there's no aha experience, then it isn't true learning.
Yeah, I agree with that totally. And I really think that great teaching is about, as you say, it's almost replication. It's like, come take my hand and follow me, and you can see the wonders of this tour of exploration that the originators saw and that I sometimes can see. There's just to use an obvious. You talk about some interesting synergies and that's not the right word, but the richness of various mathematical concepts. For me, as an amateur, a mere economist, when I remember taking a high-level statistics class, and we proved the central limit theorem. And it was a beautiful proof. I don't remember the details, but it was a beautiful proof. And then he said, well, let's prove it a different way. And I think we proved it three ways. We proved it once with, I want to say, do you know what we would have used? It's some kind of functions, Eiger function. What were they? I can't remember. But when we saw it proved again using a totally different mathematical framework, there was it was so moving again. It was so wow. And again, I think, to go back to Fermat's last theorem, again, even worse amateur behavior on my part, but the Takayama-Shimura-Weil conjecture, which which Wiles uses to prove it, which of course had nothing to do with number theory, right? And it's like, oh my gosh, this window opens up a different view into that extraordinary world. And that moment of human, and you have to call it creativity, is just, it's awe-inspiring.
That is the essence to me of creativity. It's that opening up of this totally new view. But you know what I would like to add to saying is that in order to have these kind of creative insights, you have to be prepared to pay the price. And the price means you have to go into you have to be prepared to grapple with difficult ideas. It's not all smooth sailing. Originally, these creative insights came out of, in Byers' case, he totally isolated himself from the universe for 6 years.
It's brutal.
But I think, so I often point to, people think that genius is a question of raw intelligence. Just some people are smarter and some people are dumber. But I think there's a lot to be said for what I call frustration tolerance. Mm-hmm. The ability to stick with a difficult situation until it resolves itself. You can't say that you personally resolve it because, of course, it's unknown. You don't know exactly which way you're going. It does sometimes seem to be to resolve itself in that flash, in that moment. Aha! Now I see it. And I think sometimes I'm thinking in particular of Isaac Newton, who seemed to have the ability to hold these problems, what he said, in front of his mind's eye, and for periods, for days, for weeks, for months, perhaps. And in Weil's case, it was for years. Until somehow, that flash came. Now, the which of us have that ability? My students, if it doesn't work out in the first 5 minutes, they were inclined to give up. Was it a lack of self-confidence? Was it, it's hard to know exactly what it was. But how many of us are prepared to live with an unresolved situation over a long period of time? That's hard to do.
Yeah, and in case of Fermat's last theorem, there was some chance, I suppose, that it wasn't true.
Of course it was. Otherwise, right? Why would you want to do it?
Right, but no, it was kind of a tour de force, right? You sort of assume it's true, and now we got to figure out how to make it ironclad. But of course, that's not true. It might not be true.
There was a lot of numerical evidence, you know.
I understand, but there's always some uncertainty.
Absolutely, that's the whole point. When you're doing you're studying an unsolved problem in mathematics, you have to guess. What's your gut tell you? It's true. True. If it's not true, if your gut tells you it's not true, you look for a counterexample. If they tell you it's true, you think, well, how could I get an argument that would prove it? So you're moving in two totally different directions depending on what you guess.
Yeah.
You have to make that guess before you start.
Let me say one more thing about learning, because I think what you said earlier is very important in terms about both the fact that it's a creative act and that it requires patience and it requires a tolerance of frustration. One thing I tell my students, and it's not very helpful, and maybe I shouldn't tell them, but I do tell them, I said, the way you learn economics, and when I mean that, I mean the intuitive side, not the formalism side. The way you learn the intuitive side of economics is by looking off into the distance and thinking about things and struggling with problems and puzzles and weighing different possible answers and looking for holes in them. And there's different ways to do that. You can do it by looking off in the distance. That's very hard. A cheaper way for most people, a more tolerable way, is to argue with people about it. So I always encourage my students to get into study groups. And of course, some of the reason I say that is because that's the way I learned in graduate school. Our study groups were extremely important.
Absolutely. I couldn't agree more with that. In fact, I think it's true for many scientific theories, and it's certainly true for mathematics, that people seem to think that it's something that you have to do by yourself. And they don't realize that by entering into, most people have this idea that they've never discussed mathematics with anyone. These are students who studied mathematics for years and years and years. They think it all happens in isolation at home at their desk. But in fact, I also always encourage students to form study groups and talk to one another, just trying to explain how you understand it to someone else is very beneficial. That's why it's great to write a book, because you're trying to figure it out for yourself, you know?
Well, to me, there's sort of that. I'm going to now posit three ways you can learn. One is you stare off in the distance and you think real hard, which is very hard for most of us to do for anything more. 6 years would be a really long time, but even 10 minutes is hard for some of us. The second way is to talk about it, and that's what this program is, right? When it goes well, it's two people sharing ideas, and the listeners are experiencing that experience through our eyes and voices and creating that learning experience. The third way is to write it down. And I think it's why I really believe it's important to write clearly, and that people who do not write clearly often don't fully understand what they're talking about, haven't fully grasped what they think they do. And by writing it down, especially writing it down for someone who's not an expert, you are forced to come to grips with it yourself. And I think those are really the ways we learn. We learn by talking and explaining to others. We learn, which is either can be done by writing as well. And, for me, that's why blogging has been so useful. It's a therapeutic way to explore ideas in print with a little bit of a check because other people are reading it.
I agree, and certainly I think that my experience with writing, which I came to relatively late in my life, to writing in words rather than mathematics, is just a very interesting process. I think it's a form of thinking. It's a form of thinking, and it doesn't. I never write as though what comes out the first draft is what ends up. It's certainly it's continually revisions, throwing stuff out, But I learned something has been wonderful for me when I started to write. I always thought that it was a question of either succeeding or failing. So either you wrote wonderful stuff or you wrote garbage. And sometimes I would have this terrible day, fairly frequently, where I would not get one decent sentence down on paper.
Yeah.
It was just, when I looked at the next, it was just embarrassing and bad. And I used to, because I brought up, I've gone to school and been brought up in a very sort of competitive intellectual atmosphere, and I always think it's a win-or-lose situation. What hit me when I started to write was I almost invariably found that the day after the bad day was a good day. And I realized then, and it struck me like a thunderbolt, that the good day was connected to the bad day.
Yeah.
That I thought the bad day was a total waste, but it wasn't. Somehow stuff was still going on in my mind overnight or whatever.
Yeah.
I slept on it, and the next day, as though by magic, the whole thing worked itself out.
Yeah. No.
And that was a really good feeling, you know. And I think that, to go back to students and learning, I think one thing that students have to do is have a little bit more self-confidence in the process, in their own processes. And I know in mathematics, students often quit because they're always judging themselves. If there's a certain very small problem and they don't get it, all of a sudden they think, oh, I always knew I was too stupid to do this.
Yeah, I'll tell a story that it always makes me a little bit sad, but it's a powerful story. One of my professors at Chicago was Sherwin Rosen, a wonderful economist and a slightly outside the box thinker, and for that reason, all the more thought provoking. And he told me once that when he had taken the core exam at Chicago when he was a student there, I don't know if this is true verbatim, but this is what he told me. He said that after the exam was over, that Milton Friedman had talked to him and said that he should become a plumber.
Oh, dear. And
I don't know whether that was a joke, but I don't think Sherwin took it as a joke. I think it was a devastating comment, and I think it created, for better or for worse, a lifelong insecurity about his ability, which we all have, right? It's one of the most remarkable things about skill and ability and mastery is that, Bill Russell, one of the great basketball players of all time, used to throw up before every game because he was nervous. And you think, how could one of the greatest players of all time be nervous? And the answer was he was nervous about living up to his own expectations and the people's expectations around him. It doesn't matter how great you are.
Maybe being nervous was part of what made him such a great basketball player.
Oh, there's no doubt about it. So when my students tell me, or friends tell me about experience, they say, "Oh, I'm really scared." I say, "That's good."
Right, exactly. I mean, I think it's not these negative feelings. I think the trick is to be able to channel them in a positive way. So it's not a question of whether you're feeling insecure or not. It's what are you going to do with that insecurity?
Right. Give up? You're going to give up, or are you going to redouble your efforts?
Exactly. And I think that it's if a teacher can lead a student to accept these so-called negative things that happen and learn to use them, to work with them, rather than just giving up on the situation, and that's a life lesson that's beyond mathematics or economics. It works for everything.
Yeah, that's deep.
In my experience, that's the key to creativity. It's using these, not expecting yourself to come out with something that's brilliant every time, but using whatever comes up in a productive way, even the so-called failures and negative states, etc. I think if you really create, there are no failures.
It's a dramatic claim. I'm not sure that's always that's true, but I think.
Well, it depends on what you mean. Of course, I can give you a counterexample, and it was meant to be dramatic in a way, just to counterpose it to the normal way of looking at learning, which is algorithmic. If you're doing a multiple choice exam, then failure is obvious. It's defined by what percentage of the boxes you've ticked off in the right way. Once you start talking about creativity and creative insights, you're in a totally different universe.
Yeah, it's true. Before we leave this topic, I just want to say, again, self-referentially, which is one of the themes of your book, which I don't know if we're going to have time to talk about, but which I enjoyed, this idea that the observer and the participant have two different perspectives, and sometimes when we're participants, we step outside. So here we are having this conversation about that thinking and writing is an evolutionary dynamic process. And of course, this podcast we're doing the same thing. When I read your book, I had a lot of ideas along the way while I was reading it, and it of course It provoked thought. It's a thought-provoking book. I didn't think about teaching when I was reading it, but in our conversation, suddenly an aha happened, and I realized that it illuminates this trade-off between formalism and wonder, and I hope it'll remind me to be a better teacher the next class I teach. But this conversation itself is evolving in a direction I didn't plan, which is more interesting probably, I hope, for the listeners, and certainly more interesting for me.
Well, I think it's very interesting, and thank you for your comments. What I think you're saying is that this conversation, and any conversation, is a creative activity. And it's so obvious, but people don't think about that like that. A dialogue, we haven't rehearsed this, right? It has a certain spontaneity. When I respond to a question you ask or a comment that you make, I don't think it out ahead of time. It just comes out in a kind of spontaneous way.
And, of course, there's different ways to run interviews. I've been interviewed where it was clear that the person doing the interview wrote down 8 questions, and they just go through them. They ask the question, they hear your answer, they tick them off, and when they get to the 8th question, they're done.
Exactly, and you could have given me 8 questions, and I could have written out the answers to those 8 questions,
and
you would phone me up, and I would have read out my answers, and it would have been the conversation would have been qualitatively totally different.
Yeah, absolutely.
I find out when I lecture, if I'm insecure and I write it out word for word and I read my lecture, it is invariably boring.
Yeah, absolutely.
I have to allow myself to enter into the uncertainty of the situation. Of course I think about it, but I never know what's coming out. It leads me in one direction or it leads me in another direction. And that's where the life of these talks, and if you allow that to happen, I think, then people respond in a much more positive way.
Well, it depends who the lecture is in front of. A lot of students resent that, and they write, I know because I've seen the course evaluations, they say things like, Professor Roberts goes off on too many tangents. But to me, those are the best parts of the lecture. They're not really tangents. They're unplanned. There's something where I have a spontaneous insight on the moment about a relationship between something I'm talking about, something I hadn't seen before. And for some students, I think that's the best part of the class. But for others, it's like, you ruined my notes, And again, it's...
And I've had students say to me, about professors that they like, this one gives a really good set of notes. I think, these students have been programmed by years and years and years of education to expect a certain thing, and also by what you were mentioning before, by the examination system, by how we test knowledge. We don't test the ability to apply the knowledge that we've covered in class to a new situation. That is a different story than just testing for the acquisition of knowledge. Yeah. I've had many discussions about computer knowledge, taking a course on the computer and and then what that is and how is that education compared to having a class with an actual human professor.
Well, that's why I think distance learning, which is somewhere in between, right? You're watching a professor as opposed to being in the room. It's harder to interact, and of course, they're trying to improve the ability to interact. But the idea that you could take a class from a distance via an algorithm. Once you understand this, you move on to that. That works for some types of knowledge, but for most interesting types, that's not a good model.
Well, you're certainly not going to get, that's not going to be very good at conveying the insights. You're not going to get aha moments. You are going to amass a certain amount of formal, factual knowledge in that way, which is probably a basis, But if you don't take the next step, if you never get a feeling for what's going on, I think a good way, I often say to students, to think of this, if you're exposed to something, some sort of technical argument or something like that, it's often very detailed and goes on for pages and pages, and you have to ask yourself the question, what's really going on here? And that's related to what you were saying about popularizing material and being able to understand material well enough so that you can explain it to a non-specialist. I think that, in fact, there is a huge danger with what you could call the cult of expertise, that there are these, really smart experts out there who can do the thinking for all these ordinary people. I think people are too willing to give up their human capacities of judgment to some sort of anonymous authority. And it's also true that just because a whole bunch of people is smart does not mean that they don't all subscribe to the same orthodoxy.
Yeah, well, groupthink is a big problem, obviously.
Sure, it is, and it's if you get promoted and get money on the basis of thinking like everyone else, why would you want to think differently?
Yeah, we raised this issue in a couple of podcasts. Freeman Dyson and Ara Rubinstein. If you want to go back, listeners, we'll put links up to those, and you can listen to those podcasts as well. Talk for a little bit about the implications of this for both the public perception of science and for the act of being a researcher and scientist. One thing you're saying, obviously, is that we should be a little skeptical about claims of certainty. What else are some of the implications? And by the way, that also, what I find is that scientists today are so uneasy with this debate between so-called debate. I don't see it as a debate, but the so-called debate between religion and science. That if you say anything about science being uncertain, you're giving ammunition to the enemy. The enemy is the anti-rational, so-called anti-rational, so-called religious folks who are anti-science. And for me, I don't see any conflict between the two. But I do think that scientists make bolder claims than they are entitled to, simply because they don't want to even open the door to this ambiguity and uncertainty which you're talking about in your book. So talk about that.
I agree completely. It is a problem. I think, by the way, that it is a particularly, although it's an international problem, talking to you from Canada, I don't feel it's as an acute problem in Canada as it is in the United States.
That's correct.
There is a certain particular debate that's going on, and it's been interesting for me to get responses from my various books from Americans, and you described it perfectly. People are terrified that if we talk about any kind of limitations to the scientific method, that we're sort of embracing a kind of religious fundamentalism.
Which is bizarre.
I think just that's a terrible mistake. I think religion has insights to contribute to the human experience, and we get off on a tangent. It means whenever we have a kind of ideology and we don't allow people to question it, then it's a negative thing. And I think turning science into an ideology is not going to help anyone. Of course, it's clear which side of that argument I'm coming down on. I want to loosen up what some people feel science is all about. I want to say, to speak on behalf of what I think is the larger human potential. I do not believe that, for example, when it comes down to evaluating nuclear energy, to just pick something out of a hat, that ordinary people, it's not just for nuclear engineers to make that decision. It's, unfortunately, someone has to explain it to the population in such a way as so that they can think about it and make an informed judgment. I think this question of giving up that your ability to make judgments because, quotation marks, it's scientific or it's mathematical, and I think mathematics plays a big role in that. It did, I think, in the financial crisis, and I think it does in general because people have the feeling if there are equations, if there's mathematical formalism, they will never understand it, and therefore it's beyond their abilities to even enter into the question. So people very often opt out of decisions that are vital to their lives.
And they assume that those equations, because they have Greek letters and equality signs, must be truth, which is a bizarre...
They assume, in fact, that's right. And by the way, I think that... one of my things that I flog all the time is the misuse of mathematical formalism. The idea that by converting a very vague situation into mathematics, that all of a sudden it now becomes truer. We all know that your models are only as good as your assumptions. And every piece of mathematics is based on assumptions. And you have to go back and question the assumptions that people make. And the assumptions are generally not discussed. In a mathematical situation, there's always various axioms floating around. Well, look at the axioms. And, so if the way that the mathematician wins arguments with his wife, sort of, for example, is you get her to agree to a set of axioms. And then you show by logical reasoning you end up where you wanted to end up in the first place. There's something a little unfair about that kind of reasoning. That is that, in the computer science, they know it very well because with this expression, garbage in, garbage out.
Yeah, well, in economics, we do the same thing. We want to get to a conclusion. We figure out what the model has to be to get there. And that's what I think is a destructive way of having intuition about the tools.
But often, that's the way it's done. People don't realize it's you pretend. What you actually do is you reason backwards and then you recreate it forward.
Yeah, and that gets to your point about the observer and the participant and sciences.
I think, we all have this role. I mean, it's interesting. This conversation was a conversation, although we were talking about science and about economics and about, so in a certain sense it was from the point of view of the observer, yet we ended up discussing our own experiences as teachers and researchers, et cetera, et cetera. So that was from the point of view of the participant.
Yeah.
And I think actually you get to a deeper truth by accepting the fact that we have these two ways of looking at things than if one just denies the existence of one or says that one is just sort of not part of science.
Well, we had Ed Leamer on the program, a very thoughtful econometrician who wrote a very provocative paper called Let's Take the Con Out of Econometrics, where he basically makes the very important point that when you have lots of freedom to reject equations that you don't like the conclusions of, the standard statistical tests that are used then to evaluate the statistical significance of any one that you do accept is doesn't hold any longer. And I've suggested, he suggested, I'm going to give an extreme version of his ideas, but what you could imagine is you should video yourself as a researcher looking at all the different possibilities and watching as a consumer of the research then the equations, the models, the formulations that were rejected, not just the ones that ended up as the final version that confirms the result, but all the ones that had to be rejected and why they were rejected. Mm-hmm. That's an outlier. Got to throw that one out. Of course, you don't see that in the process. So it's basically saying, we ought to let our fellow researchers into the kitchen alongside us to see how we did the cooking. But I want to end on
That's a radical idea.
I know, and it's very time consuming. The simple version of it is to make sure people can at least can replicate your results. That's even hard enough. Is the tragedy in economics, and it's hard in science too.
But what you're saying is that's really important because in fact the negative experience that people have, is vitally important. Everyone knows if we did an experiment, we threw out all the outliers. Of course, it'll be statistically significant. I mean, you can make a posteriori, you can make anything into something that's significant.
I think what we need is a journal of insignificant results, because that's the real problem, right? You don't get a lot of fanfare for publishing something that shows that something doesn't have an effect, and yet, as you point out, that's an example of a failure in some dimension that's very educational, and you learn a lot from those as the researcher. But by not sharing those with the reader at the end of the thing, you make the whole process look like it was this seamless, beautiful journey that had no zigs and zags. It was just a straight line. It just went from A to B.
Well, maybe that's an argument for having scientific publications, giving them a different and alternative format. maybe in our emphasis that truth equals formalism and compression, we lose the essence, the human essence of what's going on in research.
Yeah, now that we have the web, the fact that these articles would be a lot longer in that appendix that showed all the results that didn't work out, it's a lot cheaper to do that. So maybe we can head in that direction.
Yeah, maybe there's room to do that. It's interesting.
Okay. So we're out of time, but I want to ask you one more thing because you're one of a string of guests I've had on lately that confirm my biases, and part of what we're talking about here is confirming one's biases. So I have a strong belief. I think it's not just a bias, but a view that our knowledge is limited. It's a very Hayekian view. Listeners know I'm a big fan of Hayek, but Hayek talked a lot about what he called in his Nobel Prize lecture, the pretense of knowledge, the idea that we have things that we pretend are true. So that all of what you're saying resonates very deeply with me, and it confirms this view I have. So I want to challenge you, not me, because you're the guest. Maybe I'll talk about it another time, but I want to challenge you to think about, well, what would somebody say on the other side? What would somebody say who disagrees with you? Somebody who thinks you're either overstating the case. Certainly, that's all we've got is reason. Isn't it just? Shouldn't we just plow forward and your whole perspective is just too squishy and not scientific?
Absolutely, and it's interesting because I don't have to respond to that. I can respond to the part of myself that agrees with that. After all, I have a PhD in mathematics. Why did I go into mathematics? Because I had this view of this perfect world where you could rigorously say what is true and what is false, and the world was very neat. And I'm still excited by scientific theories of everything, et cetera, et cetera. So there's a part of me that really resonates to that other point of view. I think myself now, after a lot of reflection, that view is a form of wish fulfillment, and I think I understand why people make it, because it does make you very comfortable. There are clearly certain very basic things about life that are not captured in words. And to take an example, like one's aesthetic experiences, one's emotional response to music. I think it's vitally important that we include the entire human being in our discussions of science, and not just a kind of truncated version of what human experience is. I'm probably aware as a mathematician more than anyone of the power of reason, but I think that even for mathematicians, when they want to discuss the sources of their creativity, then they're not talking about reason. That is to say, I want to say that the sources of reason are themselves not reducible to reason. So there is something, and like many, many famous scientists like Albert Einstein, ultimately there is a certain wonder and mystery associated to the natural world that you're either receptive to or not, and I think, the great ones are receptive. And then they try to work with that and put it into some more kind of concrete form, which includes rational theories. But when you look back to your sources, then you're looking, not beyond the theory so much as before the theory, before reason. So in that sense, things cannot be captured definitively, and things are, a little bit open.
My guest today has been William Byers. Thanks for being part of EconTalk, William.
Thank you so much.
This is EconTalk, part of the Library of Economics and Liberty. For more EconTalk, go to econtalk.org, where you can also comment on today's podcast and find links and readings related to today's conversation. The sound engineer for EconTalk is Rich Goyette. I'm your host, Russ Roberts. Thanks for listening. Talk to you on Monday.